Welcome to the AI Coach by Anil Nathu. You're joining us for the deep dive, where we take complex ideas, extract the most important nuggets of knowledge, and give you a shortcut to being well-informed. Today, we're plunging into a really groundbreaking area of artificial intelligence. Our mission is to understand a new approach to AI cognition, one that promises to fundamentally transform scientific discovery and, well, even how we all interact with intelligent systems.
And our source for this deep dive is a very recent, and I think incredibly significant, paper from Microsoft Research. It's titled Cognitive Loop via In-Situ Optimization, Self-Adaptive Reasoning for Science.
Oh.
The authors, Newman Cheng, Gordon Broadbent, and William Chappell, they introduced this new framework, CLIO. And CLIO really stands poised to tackle some of the biggest challenges in making AI truly useful and, maybe more importantly, trustworthy for complex problem solving, especially in these high-stakes areas like, cutting-edge scientific discovery.
Yeah, and as we unpack this, I think you'll find some truly surprising insights into how AI can work with us, not just for us. This deep dive is all about building AI that, well, not only thinks smarter and gets more accurate answers, but also openly shows its work, signals its uncertainties, and crucially, lets us step in when it needs a nudge in the right direction. It's about bringing unprecedented transparency and steerability right to the forefront of AI. And that's really a core philosophy behind what we explore and aim to simplify at AI Coach by Anil Nathu.
The problem CLIO solves, beyond current AI limitations.
Okay, let's unpack this then. The authors of the CLIO paper, they immediately set the stage. They describe the current AI landscape and, more importantly, pinpoint exactly why existing approaches often fall short, particularly for these high-stakes applications like, rigorous scientific discovery. What exactly are these fundamental limitations they're highlighting?
Precisely. The paper points out two main categories of existing AI development that CLIO aims to move beyond. It draws a clear line. First, you have frameworks built over what they call non-reasoning models. Think powerful large language models, right? But the way they approach problems often bakes in these preconceived assumptions. Assumptions about how humans should think or how problems should be solved. Their approach is, well, somewhat rigid. It's predefined by the model developers, like following a script, really, rather than adapting on their own.
Okay, so that's one type. What's the second?
The second category they identify is existing reasoning models. Now, while these are designed to perform complex logical steps, they often abstract away precise control. What this means in practice is that the end user, whether that's a scientist, a researcher, or anyone, really has very little say in how the AI arrives at its conclusions. You get the output, the final answer, sure, but the intricate multi-step thought process, that remains largely a black box.
Ah, the black box problem. We hear that a lot.
Exactly. And the core issue, as the authors explain it, is that for scientists to truly maximize AI's utility in cutting-edge research, they need more than just accurate answers. They desperately need transparency into the AI's reasoning, to understand the logical steps it took, where it might have gone wrong. And, perhaps most importantly, they need steerability. Think about these long-running, high-value tasks dedicating an AI to creating new materials or discovering novel drugs. The AI's fundamental reasoning strategies are largely dictated by the model providers in current systems. These existing systems are based on what they call post-training cycles, meaning once they're deployed, their fundamental reasoning patterns are essentially set, baked in. The paper says these models are relegating them to steer behavior utilizing the context window alone.
Okay, context window alone. What does that mean in practical terms? How limited is that steering?
It means users can only influence the AI's next step, usually by crafting very careful prompts. You can nudge it, but you can't truly intervene in its ongoing internal thought process in real time.
So the AI does its thing, delivers an answer, and you're left to observe. You can try to nudge it a bit with your next prompt, maybe rephrase the question, but you can't truly guide its thought process while it's happening. What's the real-world impact of this? How might this limitation actively hinder a scientific breakthrough?
That's a critical question. Imagine a scientist using AI to design a new drug molecule. The AI suggests a promising candidate. Great. But then that candidate fails in the lab. If the AI can't show why it chose that specific structure, the scientist is left guessing. Was it a logical flaw? Did it overlook some subtle chemical principle? Did it just not consider other options? They can't easily intervene and say, okay, AI, interesting, but what if we prioritize stability over potency right now? Current models just don't easily allow that kind of dynamic, iterative guidance.
Right. That lack of real-time control sounds like a huge bottleneck when you're dealing with scientific unknowns. The path is rarely straightforward.
Exactly. And this is precisely where CLIO comes in. It's positioned as a truly transformative solution. It's introduced as an alternative approach that enables deep and precise control over the reasoning process. Think of it as empowering LLMs to self-formulate ways of approaching a problem, adapt behavior when self-confidence is low, and ultimately provide scientists with a final belief or answer. This goes way beyond just prompting an LLM. It gives the model the capacity to intelligently orchestrate its own complex problem-solving approach from within.
That's fascinating. So it suggests a much more dynamic, responsive AI, one that acts more like a cognitive partner than just a tool. What does this mean for the development and life cycle in scientific research? Are we talking about compressing years of work into months, or even changing the types of problems scientists can tackle?
It absolutely changes the paradigm. The paper emphasizes several key advantages that redefine that human-AI collaboration, and yeah, the development cycle too. First, CLIO allows for self-formulation. The AI isn't just following a script. It can generate its own unique, diverse approaches to problems, like a human brainstorming multiple strategies, and that's built into its design. This really speeds up the initial exploration phase.
Okay, self-formulation. What else?
Second, it adaptively adjusts its behavior, especially when its internal confidence is low. If it senses it's on shaky ground or current reasoning isn't robust, it can pivot or reevaluate. Much like an expert human might, reconsider their approach midway through an experiment. This self-correction ability dramatically reduces wasted effort and speeds up finding a solution.
Makes sense. Fewer dead ends.
Third, and this is critical for trustworthiness, its open design means you can actually observe its uncertainty levels. You can understand how its final belief states are formulated, often through visualizable graph structures. This provides unprecedented transparency, moving from a black box to more of a glass box. For a scientist, this means understanding the logic behind the AI's suggestions. It allows for, essentially, peer review of the AI's thought process itself.
That's huge. Peer review for AI thoughts.
And fourth, this is really revolutionary for practical use. Scientists can interject corrections, either in real time or after the fact. That capability is largely absent currently, where influence is limited to the next prompt. This means a scientist can literally debug the AI's thinking, say, no, that's not right for this biological mechanism, go back, consider X instead. This iterative human-in-the-loop steerability is what truly compresses research timelines. It makes complex, high-value problems that seemed intractable, well, potentially solvable now.
And here's the kicker from the abstract, the bit that makes this sound so efficient. CLIO achieves all this without any further post-training. That implies incredible flexibility and efficiency. No need to retrain a massive model, which is usually hugely expensive and time-consuming, right?
That's absolutely right. It's a game changer for accessibility and rapid deployment. And the authors back this up with impressive initial results. They tested it on a tough benchmark. OpenAI's GPT 4.1, a powerful LLM but not primarily a reasoning model when enhanced with CLIO, achieved an accuracy of 22.37% on text-based biology and medicine questions from Humanity's Last Exam, HLE. Now, that's not a small gain. It translates to a 13.82% net increase, or a staggering 161.64% relative increase compared to the base GPT 4.1 alone.
Right.
And get this, it even surpasses OpenAI's O3 performance in both high and low reasoning effort modes.
Wow, it beat O3, but O3 is designed for reasoning, isn't it?
It is, which is particularly notable. It clearly shows CLIO's capability to significantly boost a non-reasoning model's performance just through its in-situ optimization. It transforms it into a formidable problem solver without needing a massive, data-intensive retraining process.
So what does this all mean for you, our listener? Whether you're a researcher, a strategist, or just deeply curious about advanced AI, imagine an AI assistant that doesn't just give you incredibly accurate answers, but also lays bare its entire thought process, letting you jump in, course correct, or understand why it's confident or uncertain. That's the power CLIO hints at. For your own projects, your deeper understanding, your team's innovation, this focus on transparent, controllable AI, that's a core philosophy behind how we empower you at AI Coach by Anil Nathu.
The foundation. Prior reasoning approaches and knowledge evolution.
Okay, so it's clear CLIO is stepping into a crucial gap, offering dynamic control, transparency. But to really grasp its genius, we need to understand the landscape it emerged from. What were the main methods AI researchers were using for reasoning and knowledge evolution before CLIO? What were their limitations?
Well, what's fascinating is how the paper anchors AI cognition in an analogy to the human brain right from the start. They talk about the neuroplasticity of the human brain, referencing foundational work. They emphasize how humans learn not by being static, but by adapting, creating, modifying neural connections based on experience and feedback. It's not a one-and-done thing for us, is it?
Definitely not. We're constantly learning, adapting.
Exactly. And building on this, the authors highlight how AI systems, to truly think more like humans, must similarly formulate different approaches to problems, receive external feedback, and subsequently pivot strategies. This ability to actively search for new strategies when current ones fail, and critically, to save useful patterns for later. That's crucial for scaling knowledge, moving beyond isolated problem solving to continuous growth.
Okay, so that's the human benchmark. How did previous AI systems try to achieve that kind of adaptation?
Well, the cornerstone of current AR models, especially for refining behavior after initial training, is reinforcement learning, or RL. This is where models learn through trial and error, optimizing actions based on rewards for good behavior and penalties for bad. The paper discusses several key variations. There's RL with verifiable rewards, RLVR. This uses external objective feedback, like did an LLM-produced code segment compile successfully? Yes or no, clear signal.
Right, very objective.
Then there's RL with internal feedback, RLIR. This relies on the model's own internal confidence signals, its self-certainty. The goal here is to reduce dependence on constant human feedback by letting the model estimate its own success. And of course, the most widely known is reinforcement learning with human feedback, RLHF, that explicitly integrates human input people ranking or rating AI outputs to guide the learning.
So these are powerful, widely used techniques. They've driven a lot of the AI progress we see. But the paper points out a critical limitation, a kind of ceiling on their effectiveness that CLIO aims to break through.
Indeed, a fundamental limitation. The authors state that across all these RL variations, RLVR, RLIR, RLHF, for end users, the learning or reasoning process of these post-trained models is neither personal nor steerable as learning terminates once the trained model is handed to the user. That's the key bit. The specific reasoning strategies, the how it thinks, are baked in during initial training by the model providers. Once deployed, you, the user, have no direct input on how it fundamentally learns or reasons.
So if I have a really specific niche scientific problem,
Exactly. If you wanted to customize how the AI thinks for your unique lab problem, it would require further post-training. You'd need high-quality, domain-specific data. And as researchers have noted, that data often just doesn't exist for truly novel discoveries. So you're essentially stuck with the off-the-shelf reasoning without the ability to dynamically adjust its core cognitive patterns. That's precisely the gap CLIO aims to fill.
okay, that makes the limitations clearer. Now, what about how AI systems evolve knowledge more broadly, beyond just learning from rewards or feedback?
The paper highlights some fascinating work here, like Google's AlphaVolve. This shows how AI systems can continually scale their inference time compute, basically. Keep thinking harder at the time of solving to discover or rediscover state-of-the-art algorithms through an evolutionary process. Imagine an AI not just solving a problem, but actively improving the method it uses.
So it learns better ways to learn.
In a sense, yes. A key aspect of AlphaVolve is using verifiable rewards to rank and prioritize the algorithms it discovers. This is crucial because it helps narrow the search space, reducing the burden on the LLM to control exploration. It enables this incremental evolution of knowledge from simple concepts to highly complex problem solving, building block by block, strategically.
Interesting. What other examples do they cite?
They also reference Apple's Illusion of Thinking paper. Intriguing title. It points out that models do great on problems with smaller combinatorial search spaces, fewer possible solutions or paths. But they struggle dramatically as that space grows, often exponentially, like a simple crossword versus a complex scientific mystery. The underlying idea for CLIO, by implication, is to reduce the complexity at each step, making even vast search spaces manageable. This involves different search strategies CLIO incorporates. Breadth-wise exploration.
Like brainstorming.
Exactly. Sampling many different perspectives or paths in simpler situations. And then for complex cases, depth-wise approaches. Building out specific reasoning paths, prioritizing promising ones, pruning the unlikely ones, like a researcher pursuing a key experiment thoroughly while discarding dead ends.
Got it. Breadth and depth. Now, beyond these general AI systems, the paper also discusses specialized science agents. How do they fit in?
Science agents are a really exciting development. AI systems specifically designed to assist in complex scientific discovery, often running autonomously for ages. The paper cites examples like Google's co-scientist, Sakana's AI scientist. Both show immense potential. Many of these, like CLIO, use the HLE benchmark to test their reasoning. For instance, Stanford's Bio-MNI combines an agentic system with curated scientific literature and tools to boost HLE performance. Shows how integrating knowledge and resources helps.
And are these being used in practice?
Yeah. Oh, yes. Future House's Robin, for example, used a multi-agent architecture to identify a novel treatment for dry, age-related macular degeneration, a huge medical challenge. What's even more advanced, it integrated an iterative lab-in-the-loop approach, automating parts of discovery by directly interacting with actual lab experiments, AI guiding physical experiments. We're even seeing self-driving laboratories speeding up material discovery, systems designing, synthesizing, testing materials with minimal human input. Incredible strides.
These sound incredibly powerful, truly pushing boundaries, but there's a recurring theme, isn't there? A common limitation despite their power.
Yes, a crucial one CLIO directly confronts. While these systems boost performance dramatically, the authors highlight a clear gap. They often lack critical control mechanisms for end users. That steerability issue, especially in deeply technical, high-stakes domains like science or diagnostics, remains largely unaddressed. You get an answer, often a very good one, but you can't easily intervene, understand the nuances of the AI's internal struggles, or course-correct its reasoning in real time. This lack of granular, in-the-moment control fundamentally limits their utility where human expertise and oversight are essential.
So CLIO steps right into that gap, aiming to give scientists the precise control needed for true collaboration. Okay, here's where it gets really interesting. How does CLIO actually do this without constant, expensive retraining?
CLIO's core methods, how it works under the hood.
All right, let's dive into CLIO's inner workings. How does it pull off this unprecedented control and performance without extensive retraining? That's often the biggest hurdle. This cognitive loop sounds key.
It really is. If we connect this to the bigger picture, CLIO's genius lies in its ability to leverage the inference time evaluation of progress and self-confidence to optimize thinking in real time without additional training cycles. Oh, that's a fundamental shift. Unlike traditional RL, which needs massive training data and costly post-training to refine behavior, CLIO doesn't. Instead, it relies on its internal self-confidence and reflection to reason through and adapt to problems at inference time. It's like having an internal critic and a strategic planner built right into its live operation, constantly checking its own thinking.
That's fundamentally different. It's not just pre-programmed, it's learning and adapting as it solves the problem in the moment. That makes it far more agile, more responsive, especially for science where things change constantly.
Exactly. The paper details this through what they call the recursive nature of cognition, another compelling parallel to human thought. As they note, the human thought process is not always linear, nor is it direct. Think about how you solve a complex problem. You don't just follow a straight line, right? Problem solving often requires formulating multiple paths, exploring different angles, then selecting the most promising ones. CLIO is designed to mimic this complex, nonlinear, iterative human process.
Okay, so how does it mimic that? What are the mechanisms?
To do this, CLIO possesses both breadth and depth-wise exploration capabilities. For breadth, it builds on existing ideas like chain of thought prompting, breaking problems into steps, and reasoning then acting, using tools. But the key difference with CLIO is that it does not rely on prompting to construct thought patterns. Rather, orchestration of thought is native to its design. This means exploring many different options in a feed-forward manner, generating diverse initial approaches. That's an inherent part of CLIO's architecture, not just something you ask it to do via a prompt.
Okay, so it naturally explores widely. What about depth? How does it avoid getting lost exploring one idea forever, that rabbit hole problem?
Right. For depth, CLIO introduces a novel and very clever use of recursion. It has the ability to invoke itself. This creates individualized thought channels, each with its own independent context window. This is absolutely crucial. It allows CLIO to dive into a particular area of exploration without polluting the aggregated context with incomplete thoughts.
Yeah.
Imagine you're deep in thought on one complex aspect, but still keeping the bigger picture clear without getting bogged down. This design enables thorough, focused exploration within or across these channels without the cognitive overload that often plagues LLMs when their context windows get cluttered.
Individual thought channels, like having separate scratch pads for different lines of reasoning.
That's a great analogy. And to control this depth, to prevent that exact rabbit hole scenario, CLIO can self-reflect. It determines the necessary duration or depth for its recursion. Governed by a maximum recursion or maximum cognitive depth, denoted D in their algorithm. The authors found that without this control, systems can continue to goad themselves into further exploration, leading to fundamentally incorrect results over long periods of time. It's a vital safeguard, similar to configuring reasoning effort levels elsewhere. But CLIO controls both the depth and the assumptions made at each step, and those can be dynamically altered or weighed differently, offering much more granular control tunable by the user.
So CLIO can even optimize its own internal strategy as it's thinking, in real time. That's like a scientist refining their method during an experiment, not just after it fails.
Yes, precisely. While exploring, CLIO can self-optimize its own internal strategy through a series of parameters that are editable when invoking itself. It can dynamically modify its problem-solving approach or focus as it goes. This runtime optimization directly influences its internal belief structures over time, especially when it needs to resolve self-recognized uncertainties. If it realizes a line of reasoning is getting less confident, it can strategically adjust its parameters to explore alternatives or focus on clarifying that uncertainty, all without external input.
And CLIO also has a sense of awareness. What does that involve beyond recursion and self-optimization? How does it know when it's truly done or when it needs more time?
Good question. In a section called Building Awareness into CLIO, they describe how each thought channel knows when to complete its process. They enabled a special completion function. But proper termination isn't just about reaching an answer. It requires both sufficient confidence and a temporal understanding of the progress. Just minimizing token probabilities isn't enough for thoroughness. So, to prevent premature termination, CLIO dynamically registers the special completion function only when a certain threshold of coverage was met. It only considers itself done when it is explored enough. This is critical for reducing bias, especially with complex problems having multiple right answers. Ensures comprehensive exploration before settling. Its internal attention then establishes belief about significance, akin to how humans consider diverse perspectives before forming an opinion. Ensures it's truly thought things through.
Okay, that addresses thoroughness. But what about another common AI challenge? Over-indexing, where it latches onto one perspective and gets biased, like a detective fixating on one clue. How does CLIO handle that?
Right, that's a key challenge. In overcoming the over-indexing challenge, the authors explain that agentic optimization often involves ensembling multiple perspectives to foster diversity. But selecting the best answer from these variations, especially using prompts, can inadvertently introduce bias from the context window itself. The way you ask can influence the choice. To mitigate this, CLIO leverages sophisticated graph structures to reduce noise and provide a more holistic, unbiased view of its collective thoughts.
Graph structures, how does that work?
The process uses a powerful LLM, like GPT 4.1, to perform entity and relationship extraction from CLIO's complex, multi-threaded thought processes. These extractions are then clustered unsupervised to form hierarchical communities of information, which get summarized and embedded. At runtime, these summaries and embeddings help retrieve relevant info from this knowledge graph. It transforms the messy, linear sequence of thoughts into a structured, interconnected web of knowledge, much more effective to query and analyze. It significantly reduces the chance of over-indexing on a single, potentially misleading chain of thought, like having a highly organized internal library of all its ideas.
An internal library, I like that. And this is where the more thinking knob comes in, allowing it to deepen understanding using this organized knowledge.
Yes, precisely. To build an even more holistic view, CLIO has a control knob it can turn to think more. This triggers multiple parallel runs, often with different temperature configurations, controlling creativity versus determinism. Each run produces a distinct chain of thought, a slightly different perspective. These are collected to build a joint graph using all sampled sequences, a comprehensive interconnected map of its collective reasoning. Finally, CLIO queries this comprehensive graph with the original question to produce its ultimate response, leveraging its full integrated understanding. As detailed in their algorithm too, this intricate design lets CLIO not just find an answer, but deeply understand how it got there, and critically allows human intervention and clearer understanding of its confidence. This advanced capability is something we really focus on exploring and simplifying at AI Coach by Anil Nathu.
Evaluation. CLIO's performance against the best.
So this naturally leads to the big question. How does CLIO actually perform against top AI models when tested? Especially given its strength is this in-situ optimization, not extra training or external tools which often boost other models. Does this unique approach truly deliver better results?
The paper evaluates CLIO against other prominent reasoning models using the Humanities Last Exam, HLE. Specifically, they focused on 152 tough text-based biology and medicine questions. And HLE isn't simple multiple choice. It's known for nuanced questions designed to really push AI reasoning in complex science.
And the results are quite compelling. Strong validation for CLIO's approach. CLIO, specifically GPT 4.1 augmented with CLIO, showed superior performance compared to OpenAI's O3 model. both in O3's high and low reasoning effort modes on these pass-at-one scenarios.
Okay, pass it one scenarios, just to clarify for everyone. That means measuring the accuracy of the very first answer CLIO gives. No retries, right? Why is that such an important metric?
That's exactly right. Pass-at-one is stringent because in real-world high-stakes situations, a doctor needing a diagnosis, a scientist at a critical decision point, you often need the right answer immediately. You don't want to sift through multiple attempts. It measures the AI's ability to get it right first time. Invaluable. It's a direct comparison of CLIO's efficiency and accuracy against leading purpose-built reasoning models.
Okay, so how did CLIO actually do on the numbers?
Well, looking at the data in the paper, there's a chart that really visualizes it clearly. The baseline GPT 4.1 on its own got about 8.55% accuracy on these tough HLE questions. Pretty modest. But when augmented with CLIO, its accuracy jumped straight to 14.47%, a substantial 5.92% absolute increase. But here's where the more thinking knob really shines. When CLIO used its graph-based ensembling and deeper recursion, the accuracy soared to an impressive 22.37%. That's another 7.90% jump over base CLIO, and a massive 13.82% net increase, or a staggering 161.64% relative increase compared to the original base GPT 4.1. And for comparison, OpenAI's O3 high scored 13.16%, O3 low scored 12.37 problems.
Wow, so it's not just incrementally better, it's significantly better, outperforming established reasoning models without retraining. And you mentioned it seems more stable, too. Consistency matters just as much as peak performance in the real world.
Correct. The data visualizations also show CLIO's remarkable stability. Across 5 independent passes one runs, GPT 4.1 with CLIO consistently showed fundamentally less variability than O3. Visually, this means much smaller error bars on the charts, a tighter range of outcomes. This stability is attributed to its graph-based structure. It effectively reduced sporadic noise from stronger false positive arguments, leads to a more balanced, consistent perspective. Instead of being swayed by one strong but wrong idea, the graph integrates multiple views, more robust. They also used a sophisticated search technique, drift search, on the ensembled graph to get these metrics. It combines global and local queries for a comprehensive view, enhancing reliability.
The paper also breaks this down by question category within biomed. Can you give us a few examples where CLIO made a particularly big difference, where other models struggled?
Certainly. That breakdown really drives home the impact across different scientific areas. For instance, in biomed genetics, notoriously complex field, CLIO got 7 out of 27 questions right. In stark contrast, O3 high got 0 out of 27, 0. O3 low got 2, base GPT 4.1 got 2. So a huge jump from basically none right to 7 in genetics. Similarly, in biomed biology, CLIO answered 8 out of 31 correctly. The others ranged 0 to 3. Even in biomedical ecology, CLIO got 7 out of 20, while O3 high only got 5. Across the board, CLIO consistently showed significant uplift, highlights its generalizability and robust performance.
That genetics example is striking, 0 to 7.
Isn't it? And another compelling example is in the immunology case study. Illustrates the power of more thinking on specific hard questions. For immunology questions, CLIO's more thinking for GPT 4.1 yielded 22.5% average accuracy, substantial improvement. What's even more remarkable is its effect on GPT 4.0, another powerful model, but with a lower baseline on these immunology questions. CLIO significantly boosted GPT 4.0's overall HLE performance from just 1.97% to 9.87%. And specifically reached 16.1% for immunology questions. This powerfully shows CLIO can enhance other foundation models too, adapting and improving their performance via its cognitive loop. Proves its versatility.
So what does this all mean for you, the listener? Whether you're grappling with complex data, automating processes, or just trying to grasp the next wave of AI, it means CLIO isn't just theory. It delivers tangible, significant improvements in AI reasoning and problem solving, all while offering unparalleled control and transparency. This is the kind of cutting-edge insight you can expect from us at AI Coach by Anila Nethu.
Discussion, trust, control, and uncertainty.
Okay, beyond just the performance metrics, which CLIO clearly nails, the paper delves into what I think are CLIO's most profound contributions. Establishing trust in AI's thought processes and enabling precise control. In a world increasingly reliant on AI, how does CLIO approach building that fundamental trust?
Indeed. This section kicks off with trust of thought, where the authors did a crucial study. They examined the diversity and semantic distance of CLIO's correct and incorrect chain of thought sequences, and they compare them against human annotated rationales from the HLE benchmark. This comparison helps answer that fundamental question. Does CLIO think like us, or just get right answers through weird means? And for the 34 questions CLIO got right, they did extra sampling to ensure 95% statistical power. Makes the findings really robust.
And the finding here is pretty impactful, isn't it? Directly addresses that black box issue that hinders AI trust, moves us toward understandable AI.
It is, very much so. They found that the rationales produced by CLIO are more like the rationales produced by humans when compared to the base model itself. They showed this visually, mapping the thought patterns onto a conceptual landscape. The visualization clearly shows CLIO's rationales clustering remarkably closer to human rationales than even GPT 4.1's, even when GPT 4.1 was explicitly prompted for clearer reasoning. This means CLIO, through its self-adaptive cognition and recursion, produces thought patterns that are not only effective but also semantically similar to how a human expert reasons. That fosters a deeper, more intuitive trust. When the AI thinks like us, we can understand it. Understanding builds trust.
That similarity to human reasoning is critical. It builds a solid foundation for the enabling deep and precise reasoning control they discuss next. If it thinks like us, we can better understand its logic, anticipate its steps, and crucially, guide it when needed.
Precisely. CLIO's open nature of exposing its belief state makes it ripe for control. The paper argues it's eminently important for a human to communicate their cognitive processes regarding the logic of how they achieved a certain result or the why behind a correct answer selection. CLIO is designed to put this front and center, emphasizing explaining the thought process, tracking reasoning, and crucially, raise flags when there is uncertainty, end unquote. This is vital because, as they argue, lack of control greatly reduces value in deep applications. They liken untrustworthy AI to accepting academic research that fails to meet peer review requirements. Harsh, but pointed. Current reasoning models, they say, inhibit the ability for humans to communicate and precisely correct a reasoning chain for imprecise or non-preferable paths. CLIO directly addresses this fundamental limitation, making AI accountable, steerable, and thus far more valuable.
This brings us to a really compelling case study on how CLIO manages uncertainty. That's a challenge for humans and AI alike in complex situations. How does CLIO signal its confidence, or lack thereof, in a way that's actually useful for a human collaborator?
All right, the immunology case study graphically depicts the dynamic nature of CLIO's internal uncertainty measurement over time. It's not just a static score, it's a real-time signal fluctuating as CLIO processes info. To analyze this, they ran prompts designed to extract the presence, level, and prior uncertainties CLIO had internally addressed. These created a timestamped dataset, allowing sophisticated trend analysis of CLIO's cognitive journey.
Okay, so what did these trends show?
The visuals of CLIO's uncertainty when it reaches a correct answer are incredibly insightful. One plot, correct low uncertainty and negative gradient, shows consistently low, stable uncertainty with a clear negative trend. This indicates CLIO was confident, moving directly to the right answer with minimal struggle, like an expert solving a familiar problem. Even more revealing is correct uncertainty addressed and negative gradient. This one shows pronounced spikes in uncertainty early on, but these spikes are then mitigated through CLIO's recursive thought channels, marked on the graph. This visually shows CLIO's dynamic adaptation. It hit uncertainty, used recursion to explore and resolve it, then converged on the correct result with declining uncertainty. It literally shows the AI working through confusion.
Wow. So you can actually see it thinking and overcoming doubt. But what happens when CLIO is incorrect? Does it still signal its struggles, or does it just confidently march off a cliff?
Yes, and this is where the control aspect becomes so powerful for human oversight. The bottom plots in the study show scenarios leading to incorrect answers, providing clear flags for intervention. An incorrect low uncertainty and positive gradient, CLIO has low uncertainty overall, but the trend is positive uncertainty gradually increasing. Further observation showed CLIO didn't use its recursion to mitigate this positive shift. It kept going down a path, leading it slowly astray.
Okay, so a subtle warning sign there. What about more dramatic failures?
More dramatically, incorrect high uncertainty and positive gradient shows clear signal through high volatility and continually increasing uncertainty. Wild, erratic oscillations, revealing CLIO's repeated, desperate attempts to address uncertainty but failing. This is a crucial takeaway. These oscillations are clear signals for when end users must be brought in for interaction or additional review. What's fascinating is CLIO still converges on an answer despite these oscillations, highlighting a critical gap in existing models that often just give a final answer without indicating struggle. CLIO's transparency provides that vital early warning.
And they confirmed this wasn't just an isolated immunology finding. They extended this across broader scientific domains.
Yes. Using a baseline of 95% statistical power, They found consistent observations across subdomains, like immunology and biochemistry, not just specific examples. For instance, correct samples tend to have higher initial uncertainty and higher uncertainty ranges.
Mhm.
Seems counterintuitive, right? But it suggests CLIO is willing to tackle harder problems and openly acknowledge initial lack of clarity. Critically, these correct samples show a significantly higher ratio of addressing uncertainty and hold a negative gradient in uncertainty on the path to resolution. This confirms that successfully addressing uncertainty, reducing it over time, is a hallmark of CLIO's correct answers. It works through his doubts.
So tracking the trend of uncertainty is key.
Yes, exactly. These results underscore the immense importance of a scientist seeing CLIO's trajectory and velocity of uncertainty signals. CLIO prioritizes developing escalation points that can be identified and relayed to a scientist, fostering transparency and trust. This means successful problem-solving alongside end users can be attributed to proper interjection at the right time. Incorrect or oscillating thought patterns can be terminated directly by a human, then resumed in the correct direction. Enabling efficient human oversight prevents the AI wasting time and resources on dead ends. It's a genuine partnership.
This level of control and transparency really does move AI from a black box tool to a true collaborator. That concept is absolutely central to the philosophy behind AI Coach by N. Nathu, where we believe human-AI teaming is the indispensable future of innovation.
Future work, the ACT framing.
Okay, the paper wraps up by outlining future research directions, framed by what they call the Accuracy, Cost, and Time, or ACT, framework. Sounds like a holistic roadmap. What does this mean for CLIO's continued development and its broader impact?
Right, the ACT framework. First, they discuss 6.1 accuracy. While initial tests clearly show CLIO's controls like temperature, cognitive depth significantly impact performance, more research is needed. To clarify optimal use, trade-offs for different question complexities. What's particularly promising, though, is CLIO's observed ability to effectively combine different models, even reasoning and non-reasoning ones. To answer questions individual models couldn't solve alone. For example, they saw CLIO combine GPT 4.1 and o3 to solve problems o3 failed on. Remarkable. And this extends to others, like Microsoft's 5.4 xAI's Grok 4. CLIO helped 5.4 solve new biology questions, helped Grok 4 answer an extramolecular biology question more than half the time. This suggests CLIO's broad generalizability, huge potential as a versatile orchestration layer across diverse models, getting more value from existing AI.
So it's not just making one model better, it's making any model smarter by integrating them effectively, leveraging individual strengths within CLIO's framework. Powerful vision for mixed model environments.
Exactly. Next, under 6.2 cost. They acknowledge CLIO's recursive design, deep exploration, multiple thought channels. It undeniably demands considerable computational resources and extended execution periods, compared to a simple LLM query. However, they argue compellingly this expenditure is outweighed by the potential gains in novel scientific discoveries, where a single breakthrough new drug, new material far exceeds the compute cost. And the utility isn't just science. Preliminary work suggests CLIO can extend to other domains needing deep recursive reasoning, like complex legal services or financial analytics, where multi-layered problem-solving and careful detail analysis are critical. The high-value outcome outweighs the short-term cost.
Makes sense. What about the time aspect, especially for those really long scientific discovery processes spanning months or years?
For 6.3 time, early work already shows CLIO can successfully run and orchestrate scientific tools autonomously for over 10 hours to solve complex discovery problems. Demonstrates its robustness, persistence, vital for real scientific workflows that can last days, weeks, longer. Future assessments will focus on tool integration efficacy, how well CLIO uses external tools like simulation software or literature databases autonomously, and guidance from subject matter experts over longer durations. The ultimate goal: definitively show how midstream steering influences scientific outcomes. The value of human intervention during a long AI process, not just reviewing final outputs, shifting human oversight from reviewing results to actively shaping discovery.
Active shaping, not just reviewing. Got it. Finally, they mentioned 6.4 scaling ACT. Sounds like pushing these benefits even further, maybe for training future AI, creating a virtuous cycle.
It's exactly. The idea here is CLIO's consistent ability to generate robust chains of thought, which are remarkably similar to human rationales, remember. That can be leveraged to enable downstream model training using synthetic data. Fascinating prospect for accelerating AI development itself. Instead of relying solely on expensive, scarce, human-annotated data, CLIO could generate high-quality thought processes. These then become training data for other AI models, effectively teaching new models how to reason. They're actively evaluating if CLIO's design benefits this synthetic data production and what components could ensure highest quality thought selection. It's about building AI that helps build better AI.
The ACT framework gives a clear roadmap for CLIO's evolution, pushing boundaries of AI utility and human collaboration. It's an exciting vision, one we definitely champion at AI Coach by Anil Nathu.
Conclusion.
So to wrap up this deep dive, the authors present CLIO as a really powerful alternative to post-training reasoning patterns for models like GPT 4.1. It's a significant paradigm shift, moving beyond static configurations.
So it's all about dynamic, real-time adaptation and optimization, rather than static pre-configuration or those endless, costly retraining cycles. That seems like the core takeaway.
Precisely. CLIO's adaptation at runtime leads to significantly increased performance on difficult science problems, while crucially offering the opportunity for additional control and exposure to the end user. As we move into an era of long-running science agents doing complex things, the ability for reasoning systems to be controlled, monitored, corrected in real time becomes essential. It's not just about getting the right answer, but understanding the path and being able to redirect it.
Right, the how becomes as important as the what.
Yeah.
Exactly. The authors envision replacing traditional reasoning-trained models with systems that can alter thinking patterns in real time, express the uncertainty in approaches and progress, and match the cognition approach of scientists. This, they argue, is absolutely necessary to reach the scientific potential of a human-machine team of scientists and AI agents. They present CLIO's algorithm for optimizing thinking at runtime like an expert starting from a blank slate, and demonstrate its ability to highlight its own struggles with uncertainty, apply course correction, or crucially, know when to ask for human help.
This research paints such a clear picture of AI evolving. From a black box tool to a true intelligent partner, the shift to a transparent, steerable, self-aware model is genuinely transformative. It allows for deeper, more effective collaboration between humans and AI, pushing frontiers in science and beyond. Imagine a future where AI isn't just answering questions, but truly struggling with them, allowing us to step in precisely when its confidence wavers. What new frontiers of human potential does that unlock? Not just in science, but everywhere complex problem-solving is critical.
Implementing key learnings from CLIO.
Okay, this has been a truly fascinating deep dive into cutting-edge AI, cognition, and control. Now, how can you, our listener, apply these profound insights from CLIO to your own work, learning, or projects? Even if you're not building AI models from scratch. Let's distill this into some actionable steps you can implement starting today.
Absolutely. These are practical guidance and lessons from CLIO's innovative design, applicable even if you're using, not building, AI. Number 1, prioritize transparency and steerability in AI tools. When you're evaluating or developing AI solutions, look beyond just the accuracy number. Demand systems that offer insight into their reasoning, like CLIO's graphs or uncertainty signals. Ask, can I understand how this AI got its conclusion, not just what it is? This builds trust, allows better diagnostics, enables smarter problem solving, turns AI from magic box to real partner.
Okay, prioritize transparency and steerability. What's next?
2, actively embrace human-AI teaming. CLIO really underscores that the future of advanced problem-solving is active collaboration. Don't view AI as just a replacement, see it as an intelligent partner. Design your workflows to include human interjection points, especially when AI signals uncertainty or high-stakes decisions are needed. Your informed oversight, your ability to steer the AI in real time, is crucial for best outcomes. Just like a scientist guiding an experiment, this is a core tenet of the AI Coach by Anil Nathu philosophy.
Embrace the team aspect. Makes sense. Number 3.
3, learn to interpret AI's confidence and uncertainty signals. If your AI tools provide these metrics, take time to understand them. CLIO's research shows oscillating or positively trending uncertainty is a critical flag for intervention. Treat AI outputs with healthy critical evaluation, informed by its self-assessed confidence. Can prevent costly errors, lead to more robust solutions. It's about working with the AI, not just blindly accepting its output.
Interpret the signals. Got it. Number 4.
4, think recursively for complex challenges. For multi-step, intricate problems in your domain science, law, project planning strategy, consider if the AI tools you use or build can explore problems with both breadth, diverse initial paths, and depth, focused, recursive exploration of promising avenues while managing context. This mirrors CLIO's effective strategy for navigating huge, complex solution spaces, helps break down big problems into manageable linked subproblems.
Think recursively. Good one. Number 5.
5, Explore AI paradigms beyond static post-training. CLIO shows significant gains in control can be achieved without endless costly post-training. This points to a future where AI models are more adaptable at inference time. Keep an eye on developments empowering real-time adaptation and dynamic learning in AI systems. These will offer far greater flexibility and responsiveness to your specific needs, making AI much more agile, custom-fit.
Look beyond static models.
Right.
Okay, and finally,
And number 6, visit AI Coach by Anil Nathu for further resources, deeper insights, practical guidance on integrating advanced AI principles and tools into your professional and personal life. With that continued focus on transparency, control, and effective human-AI collaboration that CLIO exemplifies so well. Outro.
what an incredible journey into the self-adaptive reasoning of CLIO. It's truly eye-opening to see how AI is evolving, becoming more transparent, controllable, and deeply collaborative with human intelligence.
Absolutely. The insights from this Microsoft research paper are a powerful testament to the value of thoughtful AI design. And I think the indispensable role of human-machine symbiosis in pushing the frontiers of discovery, ensuring AI becomes a true, intelligent partner in solving the world's toughest problems.
We really hope this deep dive gave you some profound aha moments and equipped you with valuable knowledge you could immediately apply, inspiring new ways to think about human-AI collaboration. Thank you for joining us today. Visit the AI Coach website for more AI insights.